Hello everyone, welcome to today's lectures on resonance, one of the most fascinating and important topic in physics and engineering. I am Dr. K. Nehru from Aerospace Engineering, and it's a session we will understand how system behavior when external force matches their natural system or natural frequency. Resonance is responsible for beautiful music sound, efficient ratio, or radio communication, and even catastrophic engine failure like bridge collapse. By the end of this video, you will understand what resonance is, its different types, practical application, and its significance in aerospace engineering. Let's begin. Let's first define resonance. Resonance occurs when the frequency of the external force becomes equal to the natural frequency of the system. Mathematically, the resonance condition is expressed as frequency f is equal to frequency natural, that is f is equal to f natural. At this point, every transfer becomes high in efficient, causing the amplitude of vibration to increase dramatically. Three important parameters define resonance behavior. First, the natural frequency, which is the inherent vibration frequency of the system. Second, the driving frequency, which is the frequency of the external excitation. And third, the amplitude, representing the maximum displacement from the equilibrium. When the driving frequency is below or above the natural frequency, the amplitude remains relatively low, but when both frequency matched with observed, a shape peak is vibration response. This peak creates the resonance of the system. Now coming to the other types of resonance. Resonance appears in the many forms across science and engineering. The first type in mechanical resonance occurs in the physical structures like bridge, buildings, and pendulums. When the external force synchronized with structural natural frequency, large oscillation develops. The second type is acoustic resonance. Musical instruments rely on the phenomena to amplify sound waves. Standing waves and harmonic frequency creates rich and powerful sounds. The third type is electrical resonance. In electrical circuits, especially LC and RLC system, resonance allows efficient current flow and signal amplification. Radio and communication systems use this principle for frequency tuning. Although these systems differ physically, they follows the same fundamental principle to energy transfer to matching frequencies. Now coming to the resonance mind map, to understand the major concept related to resonance, at the center is the resonance condition itself, the matching of natural and driving frequencies. The frequency branch includes natural frequency, driving frequency, and matching conditions. These amplitude branches remain as the maximum response occurs at resonance due to efficient energy transfer, and damping branch introduce concepts like energy dissipation, quality factor, and the bandwidth control. Different systems like mechanical, acoustics, and electrical all demonstrates resonance behavior. Finally, the engineering control resonance using tuning methods, mass loading, stiffness adjustment, and damping mechanism to ensure safety and performance of the system. So coming to the design thinking approach on the vibration resonance, understanding resonance is not only about the equation, it is also about solving real-time problem. Design thinking framework provides a systematic approach. First, we empathize by understanding the learning needs and practical challenges student faces. Second, we define a clear objective such as understanding frequency matches and frequency vibration amplification. Third, we ideate to create and demonstrate simulations and interactive activities. We produce prototype for the understanding of education materials include experimental and visual models. Finally, the testing comes and refine the teaching methods for the understanding of vibration resonance. This helps us to understand student-centric approach, promotes active learning and deep concept understanding. So this can be observed or measured by using a different visualization from recap to the assessment helps to understand this topic clearly. Coming to the real world application, the resonance plays a vital role in numerous engineering applications. In structural engineer, the Tacoma Narrow Bridge collapse remained one of the most famous examples for uncontrolled resonance. Modern skyscraper now incorporate a damping system to prevent similar failures. In medicine, MRI scanner use magnetic resonance principle to produce detailed image of human body. Musical instruments such as guitar and wind instruments depends on acoustic resonance to amplify sound naturally. Automotive engineers design suspension to system to avoid uncontrollable resonance. Telecommunication system use electrical resonance for radio tuning and signal filtering. These examples shows how resonance can be both beneficial and dangerous depending on how engineers manage it. So let's summarize today's session. Resonance occurs when the diving force matches to the natural frequency, to the system frequency. At resonance, vibration amplitude reach their maximum value due to the efficient energy transfer. Damping mechanism helps control this amplitude and prevent structural damage. Mechanical, acoustic and electrical systems all exhibits resonance behavior despite their physical difference. In aerospace engineering, resonance knowledge is essential for structural vibration analysis, aircraft flutter prevention, engine tuning and spacecraft component design. This key takeaway is simple. Resonance is a powerful phenomena. It can amplify performance in beneficial application or causes catastrophic failure in if not properly controlled. Understanding resonance enables engineers to design safety and more efficient and more reliable system. Thank you for watching. If you enjoy this lecture, please like, share and subscribe for more engineering and aerospace content. See you in the next class. Thank you.